Before we dive into course material, I would like to mention 4 amazing ideas or concepts that play a cornerstone role in this course. Those ideas are not obvious and not very intuitive, but they are beautiful and extremely important for signals and systems analysis. You probably have seen or maybe even used some of those ideas and concepts, but probably haven't understood or appreciated it. So here is my list of winners of the contest of best ideas of this course. First, ordinary differential equations could be solved using polynomial equations, and partial differential equations could be reduced to ordinary differential equations with one trick, which is called Laplace transform. Second, any continuous signal could be written as a sum of sinusoids. If there are discontinuity points, then it will be a sum of sinusoids for continuous intervals. Third is a definition of linear systems. Linear systems are hard to find in real life, but they can approximate many important nonlinear systems. If they can't, we could use piecewise linear approximation. Linear system is defined by 2 things. First, the response of this system to a sum of inputs is the same as the sum of responses to each input separately. Second, if the input is multiplied by a constant, the output response is multiplied by the same constant. Finally, there is a large class of linear systems that is called LTI, which has a unique property of not modifying the overall shape of sinusoidal input. Let's provide a few more details. You have probably heard about and used Laplace transforms before for circuit analysis. It worked every time, but I guess you were too shy to ask how this magic works. We know that all of the dynamic systems like electrical circuits or mechanical systems are governed by underlying differential or difference equations. Solutions of those equations are complicated and involve a lot of guesswork. Essentially, Laplace transform helps to transform ordinary differential equations into algebraic equations and partial differential equations into ODE. This simplifies significantly their solution. Let's move on to the next one. You might know already that a given function could be represented as a sum of other functions. For example, weighted sum of polynomials like 1, t, t squared, t cubed, and so on could approximate differentiable function x of t. This is called Maclaurin series, or more generally Taylor series. Let's take a simple example. Here we see Taylor series of x of t around the point A, which is in that case is 0 here. Now, pay attention that all of the x of A and x derivative of A and second derivative of A and so on, all of those things are constants. And A, of course, is also a constant. So what is left is basically polynomial in terms of t. So all of those terms will have all kind of terms of t. This one will be constant. This will be a constant multiplied by t minus a, which is first order approximation. This one will be constant multiplied by t minus a squared, which is parabolic second order approximation, and so on. So let's say we want to approximate that blue line, blue curve that we have here. This blue curve is given by some nonlinear function, for example exponent. The approximation at point 0 of first order is just linear approximation, which is just tangential line. Zeroth order approximation is just constant line. So for different n, you will have different lines which are in red color, which are showing different kind of approximation with different order polynomials of that blue line. And this is exactly what Taylor series does. Similarly, French mathematician Joseph Fourier suggested that any function could be written as a sum of sine waves. German mathematician Lejeune Dirichlet completed this work with full mathematical proof. Soon you will learn why this idea is so useful. Now let's try a simple example of approximating sawtooth wave with sine waves. We could start with adding two sine functions and get that black curve. It is still hard to believe that adding more sine waves will get us closer to sawtooth's triangular shape. Let's add one more sine to the previous two. And three more. It gets closer. Note that the original sine waves are still there. Now let's try 100 sine waves. This time we are much closer to the desired signal. If we want to use it for non-periodic function, then we can use Fourier transform with infinite number of sine waves. Most of this course will be devoted to linear time invariant systems, abbreviated as LTI systems. Many practical systems could be approximated by LTI systems. Linear systems have a very nice and convenient property which is called superposition, outlined here. Let's take a simple example. Let's say we have input which consists of sine wave and square wave. So their sum will look something like that. This signal will pass through the system that way, and the response will look maybe something like that. Now, the question is, can we compute that response based only on responses to each signal separately? Let's say we are entering only that sine wave here and get some response. And then we get square wave here. And get some response. If this system has superposition rule and this is LTI system, then the response will be basically sum of those two responses, which are separate responses to separate signals. So this signal will produce that response, this signal will produce that response, but that signal will produce some of those two responses. Alternatively, you can think about LTI system as producing the following effect. Let's say you have some LTI system like that, which is responding to some of signals that you have at the input. Now, equivalently, the response will be the same as you just replicating that system multiple times and getting list of n systems like that, and you getting responses to each signal separately from x1, x2 to xn, and then making a sum of the response. The y here and the y here will be the same for both systems. It is simple to understand that when some signal passes through the system, it is modified in some way, and different systems will modify that signal in different ways. Now I would like to ask a little bit surprising question. Is there any signal that when passing through all, and I emphasize all possible LTI systems, it will stay the same or possibly be amplified or attenuated? Which means that if some signal comes here of some specific shape, similar shape, maybe amplified or attenuated, will be appearing at the output of that system. So we want to preserve the shape. Even more surprisingly, the answer is yes. Such signal exists and it is called Eigen Function. The tricky part here is that this signal is a complex function. This is why we will be dealing with trigonometric and complex functions most of this course. So, what is eigenfunction? The terminology comes from a similar linear algebra problem. Let's assume we have square matrix A and some vector x. Let's also consider multiplication of A and x. Pay attention that if I multiply A by x, the result will be also a vector of the same size as vector x. Now the question is, what will happen if I will multiply matrix by vector? Essentially, you can think about that as basically scaling the vector x and rotating vector x in n-dimensional space. So if A is matrix n by n, then x will be rotated in n by n-dimensional space. The question here for eigenvectors and eigenvalues in linear algebra is, what is such vector x and such constant lambda that the vector will not be rotated at all. It will be just scaled, which means it will be multiplied by a constant lambda, like that. Which means multiplication by matrix A will be replaced by multiplication of scalar lambda. So, such constant lambda will be called eigenvalue, and such vector x will be called eigenvector. Now, let's assume that instead of linear operations such as matrix multiplied by vector, we have more general operation h applied to a signal x of t. This operation will be the result of passing a signal through a system. H operator is basically showing what system will do to that signal. So if h applied to x of t equals lambda multiplied by x of t, then x of t is eigenfunction of the system h, as we have here. Pay attention that lambda could be a complex number. For LTI systems, such eigenfunction is complex sinusoid, which is written here. Note that real part of that function is cosine omega t and imaginary part is sine omega t, using Euler theorem. So note that if we are entering into the system sinusoidal wave like that, the output will also be sinusoidal. It might have different amplitude or different phase, so it could be shifted in time, but it's still sinusoidal shape. Before we get to the topic of eigenfunctions, we need some basic knowledge on complex numbers. Let's try to summarize all of those points that we discussed before. Let's say we have LTI system and we have some difficult to write analytically signal which is given here. We would like to know what will be the response of that LTI system to that signal, but unfortunately we don't have any general tools to know it for that specific complicated signal, and the output is very difficult to predict. So our idea is that first of all we will describe that signal as sum of sinusoids using Fourier transform or Fourier series, and we always can do that. Now we know that LTI system is basically passing all of the sinusoidal waves just by a little bit modifying them, modifying their amplitude or modifying their phase. So what we'll get as the output for each one of those sine waves is something like that. So each wave will be scaled, maybe differently, and will have different phase from the original one. But what we know is the rule of superposition, which means that basically the output to that shape that we had from the beginning will be sum of the responses to each one of those sine waves, which means we can basically add all of those waves together, and this will be the response of that LTI system to that specific signal. More than that, the system itself, which is LTI system, could be described based on transfer function. And this transfer function could be described in Laplace domain, which is very helpful for us. Why? Because in Laplace domain, instead of complicated integration function, which this LTI function is doing, we convert it into multiplication function. which means this function will be transferred into Laplace domain. This transfer function will be in Laplace domain. And the response will be basically multiplication of transfer function by the input signal in Laplace domain. So it will simplify all of the processing and analysis of the signals and systems.